Okay, so suppose you have two groups. Let's say G and G prime. Okay, so group must have a binary operation. Let's say the operation this in is star. This one is star prime. Right? Group must have binary operation. The one on the left side is just star, and the right hand side is just star prime. Star could be addition, could be multiplication, or other funny binary operation. And then I have a mapping from the left hand side to the right hand side. Let's call this phi here. So generally this is just a mapping only. So what is really a homomorphism? Let's try to figure out here. Okay, let's say I have one element A inside G. So this element A goes to an element inside G prime. Let's call this image of A. Right? So A go to image of A in G prime. Right? So image of A is in G prime. Then pick another element B in G. And this element under the mapping, it goes to image of B in G prime. Now, since A and B are in G, what can we do with A and B? Inside G, we can multiply them by this star operation. So I can find out what is A star B then. A star B, we know this is also in G by closure. And G is a group here. So where does it go to? By the definition, it's supposed to go to image of A star B. Alright? By definition, it's supposed to go to image of A star B. Now, what is image of A star B now? We don't know anything, but if you actually just take away, I just know A will go to image of A, B will go to image of B. If I multiply them, this thing will be just happen to be image of A multiply in G prime the image of B, then you have a group homomorphism. If this is true, then you have a group homomorphism. Okay? If this is true, then you have a group homomorphism. This is not always true, no? Okay? We'll give you a few examples to see that when do you have a group homomorphism. Okay? So when a mapping is a group homomorphism, you must have this property. Okay, so let's try some simple example first and see whether we have a group homomorphism. We start with something that is not first. Let's say I'm going to consider a mapping from a set of real number to Z. And what does mapping do is image of X is equal to this. What is this here? This is actually the largest integer less than or equal to X. Okay, over here, the group is the group of real number and a group of integer. So what is the binary operation here? It did not tell you. Do you think what is the operation here? Okay, by default, the set of real number, you can add them. Your automatic form of group. The set of integer, you also can add them. Automatic form of group. Okay? Of course, you can also multiply them, but multiplication, unfortunately, don't form a group. Alright? So, the default operation is addition. So, even though it don't tell you, the operation is addition. Alright? Addition. Okay? Not multiplication. It won't form a group under multiplication. So now, let's see whether this is a homomorphism first. So let's look at some example. Okay, let's try to figure out where is the image of 2.7. Image of 2.7, largest integer, less than or equal to 2.7 is 2. Right? And what is the image of 1.7? The largest integer less than or equal to 1.7 is 1. Okay, now let's look at what is the image of 2.7 plus 1.7. Okay, image of 2.7 and 1.7 is what? What is 2.7 and 1.7 is altogether 4.4, right? 2.7 plus 1.7 is altogether is 4.4. So what is the largest integer? Less than or equal to 4.4? 4. So we know that it's equal to 4. The sum equal to 4. Now you ask, is this the same as the image of 2.7? We know it's 2 plus the image of 1.7? No, right? Because first number is 2, second number is 1. It doesn't add up. So, this is not a group homomorphism, right? It's just an ordinary mapping. It's not a group homomorphism here. Take note that the operation both under my addition now in this case. Okay, it's not always true, must be like that. Okay, so this is not a group homomorphism.